Hi everyone, thank you very much for joining. We will be starting this webinar now. I think we've got quite a few of the attendees that are expected already joined. We will have a bit of a slow introduction to ourselves anyway, so there'll be time for other people to join in and start listening to the awesome presentation that we've got. Today's topic is a new workflow for 3D thermal bridging calculations. There's three of us presenting today, myself on the SimScale side and two excellent colleagues from Beyond Carbon. We're going to just take a couple of minutes to introduce ourselves before we actually get into the main topics. So my name is Darren Lynch. I'm a solutions engineer here at SimScale. I've been with SimScale for about 6 years, and pretty much since the beginning, I've been working on architectural engineering type topics with the SimScale platform. This has been a huge variety of different things, but microclimate assessments, indoor analysis, air quality assessments, those kind of things are what I've been mainly concentrating on. So I'll ask Chris to now just quickly introduce himself, if that's okay, Chris.
Yeah, hi everybody, I'm Chris Finburn, I'm founding director of Beyond Carbon. I'm a certified Passivhaus consultant. I've been involved in Passivhaus projects.
It's me, but I can't actually hear you, Chris.
Can anyone else hear me? That's a shame. Ramya can hear me, so hopefully the world can hear
Chris as well. Yeah.
That's fine, that's great. Yes, I'm a certified Passivhaus consultant. I have a background in building services. I've been involved in Passivhaus projects for the last 8 years or so. I'm going to come on to briefly explain what Passivhaus is about later on, but my main interest is around influencing the design of buildings to be low carbon, low impact on the environment, and to be excellent places for people. And I'm here with my colleague Ramya, who's going to introduce herself.
Hi, I'm Ramya. I'm a certified Passivhaus designer. I have a background in architecture and building physics. In Beyond Carbon, I focus on analyzing energy performance, daylight performance, and I help in designing buildings that prioritize low carbon, better energy efficiency, and enhance the occupants' well-being. And I'm very excited to present this presentation today.
Okay, thank you very much for the introductions. So a little bit of added complexity on my side. I unfortunately can't hear Chris or Ramya speaking, so we're going to have to play this a little bit by ear. I've got a colleague in the background, Nagman, who will also be answering some of the questions as we're going along, who's going to prompt us through this. So I'm going to anyways introduce the SimScale platform today after going through this agenda. After that, I'll anyways hand over to Chris, so hopefully this doesn't affect us too much. So the agenda, as I mentioned, we've already done the introductions, a little bit of a complication in technical terms, but no problem here. We'll talk about who is SimScale, we'll talk about who is Beyond Carbon, and respectively, both of us will introduce our companies a little bit. We'll talk about what thermal bridges are and why they are important. This will, of course, be covered by Chris and Ramya. 3D versus 2D and thermal bridge calculations, an introduction to the new workflow, which is really what we're all excited about, of course. And then we'll go through a demonstration of that workflow in the platform. And finally, we'll have a quick summary, and as I mentioned earlier, the Q&A, and we'll talk about how you can be involved, essentially. And again, I'll use that as a prompt just to say, if you've got any questions, feel free to just pop them in the question section. We will be addressing those either as we go, or we'll accumulate them at the end and we'll address them live as well. Perfect. So on to the next thing, the introduction to the SimScale platform. So the main bullet points about the SimScale platform are here on this slide, but what I'll actually do is I'll talk about this for about 30 seconds, and then I'll actually show you live on the SimScale platform. So the SimScale platform, what is SimScale? Why are we different? What makes us special? So SimScale is actually an engineering simulation platform entirely cloud hosted. So you log in with a username and password in a cloud system, and you can do all of your thermal simulations, your fluid simulations, your structural simulations within that environment. So you just bring along your CAD and you walk away with design decisions. That's really what we're trying to accomplish. We've got one online platform with a broad physics, and all of those users have those physics capabilities. We've got collaboration and support, and we have got scalability to our name as well. So when we say scalability, what we actually mean is we can run as many of these simulations as you like. Nothing is locally installed. Everything is running in the cloud. All of this heavy engineering work that you would typically have to have big computers for are not being done locally. They're being hosted and performed by ourselves. And of course, it is cost effective. But let's talk about what that actually means in real terms. So this is the SimScale platform. You can see here it's open in a web browser, URL across the top. This is the home page of the SimScale platform. I can go to the dashboard. The dashboard is your collection of projects. It's where you do all your admin. It's where you can see the projects that you're working on, who's part of your company, and also what kind of resources you've got available to you. When you actually open up a project, maybe I open up this building envelope thermal bridging project, we actually open into the workbench. And here you can see some of those things that I was mentioning earlier. We've got full collaborative features, so you can invite people, we can give them edit access. On the right hand side, we've got support here available to you. And whenever you're ready to start a simulation, you just run those in the cloud without having anything run locally. And that is the real beauty of SimScale. So in a very small nutshell, that is what the SimScale platform is all about and what it's capable of. Now, if you follow me back to the slides, I will quickly hand over to Chris, and Chris can talk about Beyond Carbon. And again, I'm going to guess a little bit about the slide changes, but bear with us on this. Thank you.
Yeah, thanks a lot, Darren. Yeah, so a little bit about Beyond Carbon. We were set up in 2022 with a vision of reducing the impact on the climate of buildings, new and existing, the way we design and construct buildings and the way we operate them. We work across a range of sectors and projects, including multi-residential projects, student accommodation, laboratories, and then things like site-wide decarbonisation plans and strategic advice on a range of sustainability issues. And we work with quite a range of clients, including universities and colleges, local authorities, as well as working directly for main contractors and developers. Now, our main service is as a designer and consultant for the Passivhaus standard, which we believe to be the most successful standard in the world for developing low energy, low carbon buildings. Very briefly, this standard is all about really attention to detail and quality throughout the design and construction stages of buildings, and that leads to a building which performs as predicted to start with, but also it's a very stringent energy standard and pushes designers to think about all aspects of energy use, and the results speak for themselves in terms of the performance of those buildings. So to move on to today's topic, which is very much related to Passivhaus, as it's all to do with low energy buildings. The topic today is this new workflow we've been developing for 3D thermal bridges. We've really enjoyed working with SimScale and working with the SimScale platform and support from Darren and his team in development of this workflow. And the platform is excellent, and the support we've received has been superb. So we've really enjoyed this process, and what we present to you today is still in development, but hopefully you'll enjoy seeing what we've come up with and how that we think quite quickly could start being used more widely than just ourselves on projects. So firstly, we're going to look a little bit at the theory around thermal bridges and their importance in the design of low energy buildings. So why are thermal bridges significant? These charts just show the difference between two types of building. One is a high energy building. It might be a historic building with very high heat losses. And the red shows you the thermal bridges. There are a very small component of that heat loss compared to everything else. But for modern low energy buildings, and particularly in the realm of passive house buildings, thermal bridges become a very significant proportion of total heat losses. Everything else is compressed with high levels of insulation and an airtight construction. And the thermal bridges then start to become quite a dominant feature and need to be addressed and designed to be able to hit some of those low energy standards. And what are thermal bridges? Well, simply it's where the insulation is interrupted by objects that are made of more conductive materials. So that could be anything from timber to steel. And there's three basic types we might consider. Repeating thermal bridges, where there might be something like timber construction, where you have timber members in the insulation layer at regular intervals, or cladding brackets that are spaced regularly throughout the facade. Non-repeating thermal bridges are, for example, window details or parapet details, where there's a thermal bridge at that junction. There will be a linear thermal bridge, but they don't occur across the whole face of the facade. Point thermal bridges might be more of a one-off feature, such as steel posts. You can see here that supports a plant screen or a balcony connector, or similar items typically require a significant structural member that connects through past the insulation and creates this point thermal bridges. So there are three basic types, so there are overlap between them. So we talked about reasons that thermal bridges are important, and I just mentioned again, energy performance is significant when it comes to thermal bridges, and minimizing the thermal bridges can have a dramatically reduced building loads for very low energy buildings. The other key area here is condensation and mold. So thermal bridges, they reduce the surface temperature on the inside of the building, and if that surface temperature drops below a certain point, then you'll get condensation forming and you'll get mold growth. So calculations of thermal bridges then become very important, because it allows us to assess the risk of surface condensation and potential for mold growth or damage to the structure through moisture. It also allows us to quantify heat losses and optimize the design. Part L of the building regs for residential buildings in the UK now requires thermal bridge calculations to be carried out in a lot of cases. So for compliance, they are required. And if we design out thermal bridges, we can reduce building carbon emissions associated with heating and cooling. And we can also promote occupant well-being by avoiding cold surfaces. Any surface in a building which is significantly lower than the ambient temperature can produce discomfort. We might categorize thermal bridges also as two-dimensional or three-dimensional. With two-dimensional thermal bridges is where the cross-section is consistent, if you like, into the page, such as a window detail. That would be the way we would capture windows as a 2D thermal bridge. But 3D thermal bridges is where the cross-section changes over a short distance, and that results in much more complex heat flows. So in the case of a steel bracket that you can see here, a steel post that projects from the building, passes through the insulation layer, modeling that 2D is just, we'll see in a moment, is just not an accurate thing to do. We need to understand the three-dimensional heat flows through that detail. So just some examples of three-dimensional calculations. So cladding brackets, such as these are stainless steel cladding brackets installed in our Passivhaus building. You can see that on that chart that the red portion of that is the contribution of those cladding brackets to the overall U value. So it takes the U value from circa 0.16 to nearly 0.2. So it's quite a significant increase due to those cladding brackets. We need a three-dimensional calculation to capture that effect. Substructure has a number of three-dimensional calculations, particularly around columns, which pass through the insulation layer onto pile caps. That's a classic requirement, or a shear wall, concrete shear walls, which pass through the insulation layer, are also typically a 3D calculation. This just shows what happens if we try to model one of these details in 2D. So this is a steel post on a roof which punctures the insulation layer. If we model it in 2D, which is the bottom image, you end up with a predicted internal surface temperature of 12 degrees, which is way below the safe temperature for condensation risk. So that would predict condensation, and then you'd end up designing to improve that, maybe introducing additional thermal breaks or more insulation or whatever you do. There'd be cost and complexity associated with that. But if you model it in 3 dimensions, you see that actually the temperature profile is very different. That 3-dimensional effect means that the surface temperature actually is 18 degrees at that surface, which is well above safe temperatures and therefore not an issue. So that shows you the value of the 3D calculation. So I'm now going to introduce the workflow. We have developed this workflow using Rhino and Grasshopper. The reason we've come to this place is that while 2D calculations are well supported and there's actually free software for 2D calculations and many options out there, in terms of 3D calculation software, we felt that the options were pretty limited, and that the options that there were there often had fairly primitive geometry interfaces. They were generally just closed source black box software packages that didn't allow you to have any flexibility or to interact with other pieces of software very well, and they tend to be quite expensive as well. So we felt that we could do something here with Rhino and Grasshopper. Rhino is a very powerful geometry tool. It's a kind of hybrid between the sort of SketchUp with full-on kind of CAD capability. So it allows you to generate complex geometry very quickly, as well as high-quality graphics for visualizations, and it's very customizable and extendable through its API, and you can produce plugins and you can connect it to other pieces of software, and that really for us is just really key. When it's combined with Grasshopper, it becomes even more powerful. So Grasshopper is a visual programming interface for parametric design, and it allows you to carry out very sophisticated data analysis using geometry from Rhino. As of Rhino 8, it supports Python 3 scripting, which has API connectivity to external platforms, which we'll see in a minute is really crucial for us. There's also a wider environment of tools within Grasshopper, namely the Ladybug tools suite. You may be familiar with those, and I particularly mentioned Honeybee, which is an energy modeling tool within Grasshopper that allows you to carry out energy calculations. So we're excited about this because it means that we could start to think about integrating thermal bridge calculations with wider energy calculations and wider thermal performance analysis. So that's Grasshopper. Why SimScale? Well, SimScale is incredibly powerful as a platform. It's a cloud-based system, so you don't need any expensive local hardware. All of the computing power is on servers. It's got very advanced thermal modeling capabilities, meaning you can model a jet engine, you can model heat sinks for microchips. So buildings are pretty easy for SimScale because they don't move for a start. And that capability means we're excited about what other things it can do, as well as 3D thermal bridge modeling. It also crucially has the API to allow us to have those custom integrations and connect it to Grasshopper. And it's scalable, so you can run any number of simulations in parallel. You can therefore do parametric analysis very quickly by outputting simulations from Grasshopper. And it is validated against ISO 10211 for two of the methods. The conjugate heat transfer method is the one we're using in our workflow. So we know that the software is good in terms of complying with that standard. So in terms of how this fits together, we have Rhino, Grasshopper is the one environment. Rhino is used for building geometry. Grasshopper then we use for the model setup and preparing all of the data, which we then send via the API to SimScale and execute the simulations. Once the simulations are complete, we pull the data back into Grasshopper and we post-process that data, and we can then get results for our model, and then we'll be able to spit out a thermal bridge report. In terms of visualizations, we're using SimScale for those at the moment until we might start to bring some of those into Grasshopper, but the SimScale platform is excellent for post-processing visualization of results. So we're now going to give you a demonstration of the Grasshopper Rhino SimScale workflow that we've developed. Now this is still under development, but we have used it for commercial projects, and hopefully you'll see how powerful it is already and the potential for that going forwards as we develop it. We're going to show you a model based on a real project, which is a student accommodation building which has precast concrete panels supported from the main concrete frame with steel brackets. And you can see the middle image there of the yellow bracket is a fairly complex piece of bracketry with a thermal break at the back, and these have a fairly significant thermal impact on the building. There's quite a large number of them to support the the precast panels. So we needed to assess the energy or heat loss associated with each of these, and also the condensation risk. So that's what we're going to do. We're going to run through the workflow to construct one of these models, run it through SimScale, and then get some results.
So now in Rhino, we're setting up the base geometry for our detail. As you can see on the screen, the detail has the wall portion, the concrete structure, and the panel attached. The wall portion has brick, air cavity, and insulation. And these Rhino objects that I'm extruding, they are all assigned to their layers, which correspond to the material and the conductivity used. As you can see, we're building out using the dimensions from the detail rather than importing a PDF or a drawing into Rhino. The reason we do that is to make sure that we're drawing with a lot more accuracy and none of the geometry ends up snapping to a drawing layer in Rhino. This is really important because SimScale has some rules and guidelines as to what kind of geometry it accepts on the platform. Some of the rules to keep in mind are those objects accepted on the SimScale platform are closed solid poly surfaces, which means the ends should be capped and there should be no left behind lines and curves and surfaces. And all the objects are also distinct. There should be no overlaps and intersections between the objects. And similarly, there should be no gaps and voids between the objects unless it's a part of the design. To prevent this from happening, it's good to draw to a grid and snap to object in Rhino. As for the boundary conditions, any surface that comes in contact with another object of a different material, it's good to use the commands face split and breadth join. And we'll show this in the next slide. Now we're zooming in to see how the actual bracket is being modeled. So all the individual objects, for example, the steel screws, the plates, the flange, the brackets, and the thermal break, they're all just modeled with simple extrusions, and they all form solid closed poly surfaces. They're being assigned to the material layer, which is steel and thermal break. And now you can see how we're going to include an intersecting object like a screw that's going to go through the steel plate and through the thermal break, and how we're going to account using face split and then breadth joining them back to make sure they're closed and solid. So the screws are being assigned to steel, and now they are going to be split in the places where they intersect and then joined back. And in places where they cut through the material, for example, the thermal break, we're going to use the Boolean difference command and delete the layers that's going to be overlapping. So we will continue doing this in the rest of the geometry, so it's ready for import into SimScale.
Okay, so here we have the completed geometry of the thermal bridge, which has been put together using the rules that Rami described earlier. So now we have something which we know is robust, and we're ready to go on to the next stage of the simulation. But just to show you around the geometry in a little bit more detail, if I hide some of these layers, we can then peer inside and look at the main elements of the thermal bridge here. So if I remove these layers, I'll just hide this concrete panel. What you can see here is what is the thermal bridge, which is this bracket arrangement. So the blue represents steel, and you can see it's quite a complex arrangement of bracketry. There are two sort of main bracket parts. There's a web between them. There are bolts for bolting everything together to the concrete in the concrete panel, and there are steel channels that are embedded in those concrete elements. So it's complex geometry, quite a complex piece of fabrication. And at the back of that you can see this orange material, which is the thermal break, and that's designed to isolate the warm inside of the building from the cold of the outside, which is being, if you like, transmitted through this steel bracketry. So this is quite complex geometry, and it really highlights one of the benefits of Rhino. This is fairly quick to put together in Rhino and to edit and modify, and you can see how we can very easily inspect that and check that that's been correctly drawn. So one of the main benefits of Rhino is that the power of the sort of CAD element of Rhino and its ability to be able to manipulate geometry. So if I turn those layers back on and just show that last item. So the next thing just to highlight is that these objects have been colored, so you can see the different colors representing the different materials, and those colors come from these layers. Now the layers in our workflow are the way that we capture the different materials. So each layer here underneath the master layer SimScale geometry represents a different material, and you can see it's coded with the name and a conductivity figure at the end. So that is how we are controlling the material properties that go into Grasshopper and will eventually go into SimScale. And we're also controlling the material colors and how they appear in the model. I'm now going to open Grasshopper, and we can see how this geometry then is brought into the Grasshopper environment to allow us to prepare for the SimScale simulation. So here is the Grasshopper script that we've developed for this SimScale workflow. And what this does is it takes the geometry from Rhino and allows us to apply thermal properties to materials. It allows us to apply boundary conditions, and then to send that geometry and data to SimScale via the API, run a simulation, and then retrieve results. So the process is broken down to a number of steps. The first step is to set up the various settings for the model, in which in this case just involves selecting the directory that we're going to be storing the data that's produced by the model, as well as our various settings files. So I'm going to select this folder here, and you can see that path is now brought into the file. The next step is to select materials. Now you will have gathered that this has already been done within the model. So when Ramya built that model, she applied materials as she went along, which is generally how we build those models. It's much easier to put the objects onto material layers as you go, and it makes it a much clearer process. However, just to demonstrate how we would then go about adding materials, we've left one material conveniently off that list, which is the actual concrete wall and the slab and the concrete panel. So I'm now going to add that material here. So I'm going to click this button, and now if I go back to Rhino, you will see that that material has been added to the list. I'm going to change the color to dark gray, and then what I'm going to do is select those three objects like that, and I'm going to change their layer, and now they are colored with that dark gray color to denote that they are on the concrete layer, and that data will then be captured for those objects as part of the model and the simulation data. So I now go back to Grasshopper. So with the materials have all been selected, the next stage is to is called step 3, get geometry. Well, the geometry has already been brought in, but because we've made some changes to it, I'm just going to click this update button here, and that's going to run and gather that geometry, which it has done. And what we've got here, you can see 25 breps and one of them is an extrusion, and that tells us that we've captured all of those objects. We obviously can check the number in there. There is also a checking function within this component that carries out checks, like checking that all the breps are indeed closed, that there's no open surfaces in there, or that there's no intersections. So we have some basic geometry checks built into this component. So we've got the geometry brought into Grasshopper, and the next step is to generate and apply boundary conditions. we have the geometry within Grasshopper, but we now need to tell the software which boundaries are representative of boundary conditions. So the first step there is to create those boundaries. So we click this button here, and the boundaries then are generated within Rhino. If I go into Rhino, now you can see a new layer is being created on which we have all of the faces in this model, and they are all selectable. So I return back to Grasshopper. What I can now do is move to step 5, which is to assign boundary conditions. So in this step, we are simply going to be selecting the surfaces that correspond to each boundary condition. I think we have 4 boundary conditions in this model. We have internal horizontal, and you can see the conditions, those boundary conditions are set within this tool, and as well as a color that we're going to use to represent that boundary condition. And then we have internal upward, internal downward, and we'll finish with external. And again, you can see the conditions and the resistance values that are used for each of those boundary conditions. So if I start with internal horizontal, I simply select within the Rhino model these 2 faces here, which are on the inside, the warm side of the construction. Go to internal upward, and that's the direction of heat flow rather than the direction of the surface. Internal downward, and external. And on external there are 3 surfaces. Capture those. So we've now captured all of the boundary conditions and assigned them to the individual surfaces. The next step is to visualize this model. So I click the visualize button, and you can now see in Rhino that those boundary conditions are now visible within the model space. What I can also do at this point is display a legend. You can see that has appeared here, and that legend then can be used to check against the different boundary conditions that have been applied correctly. And also you can see how we've got the makings here of some quite good port graphics. So now that we have a model set up, and we've been able to visualize the boundary conditions, we move on to the simulation. And so in step 7, we are now going to package up all of this data. We're going to send it to SimScale with a set of instructions to start a simulation. So to do this, I simply double click this button, and then the simulation will run. It takes about 10 to 15 minutes for a model of this size, and then we can bring back some results. Okay, so the Grasshopper component has now told us that the simulation is complete. That took about 12 minutes, and we can now review the results of the simulation and bring them back into Grasshopper. So the first thing we're going to do is we're going to go to the SimScale platform and take a look at how the model appears on there, and look at some visualizations, and then we'll come back to Grasshopper and bring the numerical results back into the Rhino environment. So I've now just logged into the SimScale platform, and we can now see the model and simulation that was run from Grasshopper. What you can see on the left here is a similar workflow that we've just been through in Grasshopper, where we bring in our geometry, and you can see here in front of you the same geometry that we're looking at in Rhino. We can apply materials in a similar way, and you'll see those materials have already been applied via the API. We can then apply boundary conditions, and similarly you can see the same boundary conditions that were applied from Grasshopper. We can then move on to to review the mesh that was applied to this model, and as you can see, the mesh has been automatically generated with a greater level of detail around the bracket and the more intricate parts of the model. So next we can move on to the visualization of the results, and SimScale has an excellent platform for this. The graphics are really high quality, and there's lots of functionality and ways you can display the data. The simplest one is the temperature visualization, So you can see here a very clear graphic which shows the variation in temperature from the outside to the inside, and what you can see is a spot here where the thermal bridge is lowering the temperature on the inside surface. So this is very useful for surface condensation checks, or indeed actually for checking for potential condensation within a construction as well as on the surface. So we can, if we change this in translucent mode, you can see what's going on. You can see how the bracket is conducting heat through the insulation layer and causing this depression in temperature on the inside surface of the concrete. What we can also do is find out what that temperature is. So if I select that face, we can get some statistics, and it tells me that the minimum temperature on that surface is 18.9 degrees, which is well above a temperature that we might be worried about for mold risk or condensation. So as well as getting general temperatures, we can check surfaces. We can also do cuts, which allows us to peer inside the model. I can create a cutting plane, for example, in the Z axis. Let's just turn off statistics for a minute. Let's reverse that, change that to temperature, and now you can see in here a cutting plane, which if I move its position through the model, you'll see here I'm in the middle of the bracket at this point, and you can see what that bracket is doing to the temperatures through that model and how they're distorted. It's distorted the temperature field around the insulation layer. Interestingly, because of that thermal break, this temperature is reasonably warm. As I said before, that thermal break has done a good job of limiting the heat flow through there and therefore the heat loss. So that's the visualization within SimScale. There's plenty more functions within that, and we can use these visualizations for reports. We would take snapshots, you can take screenshots and import them into our report template for illustrating the results of our simulation. At the moment, all of this occurs within the SimScale platform. We do have plans to bring some of this visualization to within Rhino Grasshopper, but at this point in time, we moved to SimScale to take out the visual results and then back to Grasshopper for numerical results. So let's now move back to Grasshopper, and we can look at pulling some of the numerical data from SimScale. So to bring numerical data from SimScale back into the Grasshopper Rhino environment, we have created this component, and I double click this button here, and after a few moments it will bring in the main numerical results from that model, namely the heat loss associated with that model. Okay, so the component's now telling us that the data has been retrieved from the SimScale platform, and we now have some results brought back into Grasshopper, and we can also begin to visualize those within the Rhino model. So first of all, those results have actually been brought into our SimScale folder where we set up at the beginning of the simulation. So I've just put up the file that was created from SimScale, which shows the simulation time and then the heat transfer internally and externally within that model. So you have internal boundary conditions, you have external boundary conditions, and what you can see is over time those values converge, and they also match each other. So you can see that to a high degree of accuracy, the energy or the heat entering the model is the heat leaving the model. This raw data that can then be used in producing reports within Excel, which is what we would tend to do for commercial projects. But ultimately, of course, we want to bring all of this into the Grasshopper environment to allow us to export those reports automatically. So that's the raw data that's generated from SimScale. But we also bring that into Grasshopper as a simple numerical output. So what you can see here is the total heat loss has been pulled through. It was 18.9 watts. And we've also generated a heat loss per degree Kelvin figure, which can be used to generate a chi value or a psi value for a thermal bridge, which can then be used in an energy model. And we can, at this point, very simply visualize those results. So if I go back to our model, what I can do here is what we can then do is take those results and display them on the geometry model, which could easily be developed into a report output format. Okay, everyone. So that was the the demonstration of the workflow. And just to summarize, really, at the end of this presentation, what we've looked at, first of all, we've identified that thermal bridge calculations are important for low energy building design. Thermal bridges are a significant issue, and we need to be able to calculate them. 3D thermal bridges are a specific case of that, but there are numerous applications where those are required. And they are challenging to calculate, and we feel the current software options are relatively limited. Rhino and Grasshopper is a powerful set of tools for allowing us to build geometry and carry out data analysis, and it's incredibly customizable, so we can use that and we can develop that into almost anything we want. And when we combine that with SimScale, we then have the capacity to carry out 3D thermal bridge calculations, as you've seen. And SimScale is uniquely placed for this because of its power as a platform and the cloud-based methods it uses that allow us to do very high computational work very quickly, and also its API, which allows us to connect to Grasshopper and customize that calculation. I think you've seen that this workflow is pretty fast and efficient, and there are huge opportunities for development. So you've seen where some of those are, and we are planning lots of development of this. We want to expand this out. We've already got quite a list of things we want to do with it. Some of those future developments, including developing the user interface, so making that really clear in terms of those steps that we would go through. Automation, there's quite a lot of things that could be automated that currently aren't. For example, boundary conditions, we have a beta kind of script that will automatically detect all the boundary conditions in a model, whether they're up, down, internal, external, and then apply those automatically to the geometry without having to select any of the faces. Report generation, we plan to use Rhino to produce effectively a drawing output that is a report with all the images and results summarized, so that would then come straight out without having to use a separate piece of software. I talked about visualization as well, so SimScale is excellent. We don't necessarily plan to replace SimScale's capability, but we can do plenty with the current SimScale outputs in terms of bringing in screenshots and potentially generating our own visualizations within Grasshopper Rhino. And then the last one is a slightly outside the box idea, which is we start playing with carrying out larger modeling of buildings. So taking a whole section of a building, for example, that image you can see there is are the entire foundations of a building. Can we model that in one single thermal model and capture its heat loss in one, rather than producing a number of individual models? That might give us benefits in terms of the overall performance being more accurately modeled, and we're interested to see where that takes us in terms of other development ideas. So thank you. That is it for our presentation. I'll hand back to Darren. Hey there, Darren. Are you on mute?
Hey, it's Nagwan here from SimScale. Chris, Ramya, can you hear me?
Yes, can. Hi, Nagwan.
Yeah, perfectly. I'm just going to jump in for Darren. He's having some minor audio issues, but Darren's here. Let's run through some of the Q&A. Thank you to everyone who's been sending in their questions. We have a lot of questions to get through, okay? So I'm going to cluster some of the questions together because they're on very similar topics. And then I'll hand over to Darren at the end just for some closing remarks. A lot of you have asked about the recording for this webinar. So yes, we will give you a recording. Give us a couple of days to just process the video recording, and we'll tidy things up a bit, and then we'll send an email around. So anyone who registered for this webinar will get a copy of the recording, and it will also be available on the SimScale website under the section on webinars, on-demand webinars. So Chris, Ramya, Darren, what a exciting topic. And you know, we've had a packed house here. We've had a huge attendance, and it's probably the largest attendance of a webinar SimScale has done this year so far, right? And we do a lot of webinars. You can look at our website. So I think it reflects the interest that we have in this topic, right? And not just from the attendees, the industry as a whole. So let's jump in and take a couple of questions. So Chris, Ramya, and Darren, you were talking about the workflow itself. So you've covered this in parts already, but we had people asking the same question several times, so it's worth just covering again. People are asking about access. Okay, so fantastic what you've shown us. It looks very cool. Some people are asking to try it, even have the Grasshopper workflow shared. Is that something you can comment on now, Chris and Ramya? And then I'll ask Darren to touch on this as well at the end.
Yeah, so we are going to be looking for companies to help us in terms of testing this. So we want to have some beta testers to kind of put it through the ropes and you know, pull out any issues with it and help us to improve it. It's not, I would say, it's not quite there yet in terms of being able to do that. We need to make it a little bit more bulletproof for usability. We obviously know it and we can run it, but it's got its quirks that that we're aware of at the moment. So I think give us a bit more time. I hope within the next couple of months to be in a place where we're able to allow other people to use that workflow.
Oh, great. And also there's several questions about the computation and resources. So Darren mentioned earlier that SimScale is a fully cloud platform. It runs on core hours, GPU hours. What kind of estimates do you have, Chris, on just approximate simulation times and resources to do these kinds of calculations?
It varies quite a lot depending on the complexity of the model. So it could be a very simple model. Simple bracket, for example, would be 10 minutes, let's say. But for something much more complicated, it could be an hour or so. That's the kind of range I think we work in. We're talking, the hour would be something pretty detailed. It's when you have big objects and small objects in the same model, it tends to be slower. So if you have a big kind of concrete blocky building section, and then it's got some very thin steel sections within it, then that tends to kind of create a very fine mesh that drives that. So I'd say that's the sort of time frame.
Okay, fantastic. We have Tom asking if you can bring the results back into Rhino. I think you might have mentioned this.
Yes, you can. So at the moment, it brings just a single numerical result for the model, like a heat loss value for that, and we can display that within Rhino. Obviously, we can then develop how that gets displayed and where it gets displayed. We'll also add things like minimum surface temperatures. I don't see any reason why we can't. We definitely can pull those in, and then potentially locate them on the Rhino model itself to say where those are located. There's things like that where I think are very much possible. But yes, you basically can, and we're going to expand what data is pulled back in. Fantastic.
We have another attendee asking about meshing. Right now, obviously, that's a big part normally of any simulation. And the question is more specifically around refinements, okay, and control around meshing for complex geometries. How does that fit into your workflow?
I don't know if Darren's got his mic working again and can answer this one, but I mean, SimScale can definitely do mesh refinements. We don't currently have that capability from Grasshopper. We have to. Sure. We're going to have to explore that. But Darren, I don't know if you're back online to comment on that.
And I'll post it to Darren so he can answer just before closing remarks. But that's right. In SimScale, you do have automatic meshing, but you do have a lot of control to refine the mesh as well. Okay, let's move on. So this is another question.
Sorry, I was going to say the automatic meshing in SimScale is pretty smart as well. So, I've not had to do any mesh refinements on any of my models so far, actually SimScale has dealt with that in the automatic meshing. So it may be that there's not much required.
Brilliant. Chris, we have another attendee asking about reports, right? So in your workflow, you know, some of the stuff you mentioned about what's coming next, future development. So, you know, visualization is great. What about reporting? Would you be able to add automatic, you know, PDF reports or based on templates to the workflow?
Yeah, that's absolutely on the list. So we plan to use the Rhino layouts to generate reports. So Rhino basically has layouts that allow you to create drawings, right? So you can create a drawing with lots of different kind of viewports, like in CAD, of the model. So we plan to use that. It creates a kind of drawing, which could be a template, obviously, with your own kind of border and logo and everything. And then it will pull in the results. And there's other software packages like Flixo and others for 2D calculations that do a really good job of this. So we kind of want that as a sort of template for all the materials, all the boundary conditions all listed out, and any secondary calculations that have been done. So that's the idea, that it will come out as effectively a drawing that we then outputted as a PDF.
Great. Another attendee is asking about parametric capability when you're setting up some variables. Is that something you will include in, because you mentioned the SimScale API, right, in the workflow, and then SimScale can just, you know, altogether simulate the various scenarios?
Yeah, because what's amazing about SimScale is you can just keep clicking simulate, go, and it will in parallel run all of those simulations. So there's no kind of, this is not like a sausage factory, wait for the next simulation to be done before you can start the next one. So therefore we can just, from Grasshopper in theory, just keep saying to SimScale, do this one and do this one, and it will carry on doing them all at the same time. It's going to take some work in Grasshopper to get that to work, because we need to obviously think about how you manage all those changes in the model and the data, and relate them to the simulations. But it's kind of all there as a possibility. I think it's going to be a bit down the line before we're ready to kind of add that functionality.
Yeah, and Chris and Ramya, once you've done the simulations here, we have a couple of attendees asking about what's next with SimScale. I mean, do you carry on, just in your own experience, right? Use it, you know, when you're working on complex projects or Passivhaus buildings, do you carry on using SimScale for, heat transfer through, for example, the window construction and into the space, thermal comfort in the space, ventilation? What's your experience been on that side of things?
I don't know about you, Rami. I've not used SimScale for anything else. The only way I know SimScale is because we thought, could we use it for thermal bridge calculations? But I am aware of those capabilities, and that's, you know, that's quite exciting as well, because could be, you know, could be one of our next projects. Could be, let's build a Rhino model of a room and let's start simulating airflows in that room. Let's start simulating other energy flows in the building. So I know, Ragman, that's your platform to do all of that stuff, and we've now got a really good geometry analysis tool.
Yeah, and I have
Ramya, what's your
CFD functionality, and it's really useful. CFD and urban microclimate comfort testing, that's been very useful in SimScale. That's something I've tried out.
Okay, fantastic. And attendees can see on the SimScale website, we have a lot of content and knowledge base around simulating the indoor environment, right? Heat building envelope, heat transfer, solar radiation as well now, things like air quality, natural ventilation potential. So that's great. And you know, the work Chris, Beyond Carbon, Ramya have been doing with Darren, we've had a lot of interest this over 2 years, I think, Chris, right? That's how long we've been talking about it. So it's been building up for a couple of years. Okay, I'm going to take a couple of quick questions, and then Ramya, I'll ask you for some final thoughts, and then I'll hand over to Darren to close. Okay, so we've had a couple more people ask about meshing. I have asked Darren to mention a bit about meshing with the last his comments. We have another attendee asking about the business model, right? As a designer, can I have access to the tools, Rhino, Grasshopper, or is this a presentation or a service offered by Beyond Carbon? How does Beyond Carbon operate, Chris?
I think that's still an open question for us. We take the Rhino Grasshopper, as you probably know, is a very collaborative sort of space, and we've collaborated with others in developing this, particularly with the kind of Ladybug tools guys who are offer most of their plugins for free. So I think that's something we're still kind of thinking through. Our main objective at the moment is to develop something that works for us and allows us to do this kind of work. And then we want to be able to influence the industry. That's why I said at the beginning, we want to be influential in helping the industry build better low carbon buildings. So I can't give you an answer more than that at this point. And also that we want others to help us perhaps test this out as well, because sort of third pair of eyes is always good on this sort of thing.
Fantastic. And perhaps some closing remarks from Chris and Ramya, from both of you. And could you possibly just include a timeline? All that cool stuff you showed at the end. It's almost like a product roadmap, isn't it, Chris? What's an approximate timeline? We won't hold you to deadlines just yet.
Yeah, so I'll do my closing remarks and timeline on that. I'll start with the timeline. So I'd say some of those things are going to be down in the future because they're a little bit more speculative. Maybe the whole building modeling kind of thing, we've already started that. So that's a bit of a kind of play area for us. I think the priorities are going to be around the user interface and the reporting and getting that working, so that in what we want to be at within, let's say within the next 3 months or so, is to be able to press a button, it runs a simulation and it produces the bulk of a report that then can be PDF'd and issued to a client. That's where we'd like to be in say 3 months time. Yeah, sorry, closing remarks from me. I just thanks very much everyone for joining this webinar, and really appreciate your time. Very happy to make contact and talk more about this, and thanks very specific to Nagman and Darren for setting this up and all their support in pulling together this exciting new workflow. Ramya.
Thank you for the opportunity. This has been really interesting, working through from the beginning, developing the workflow in Rhino and Grasshopper. We've managed to make it as simple as doing the other sets of building analysis that is typical in the Ladybug components, say Honeybee or Ladybug. It's as simple as building the Rhino model using simple geometry, and now the SimScale API has helped us get the results into Rhino. We're going to try to get the visualizations and hopefully make the whole process quite seamless. I'm very excited to do more experimentation on this.
Fantastic. Thanks so much. My final comments before I hand to Darren is, yes, thank you to Beyond Carbon, Chris and Joel as well. Joe Callow, you guys reached out to us with this really cool idea, right? And it's a great example of excellent innovation by industry experts such as yourselves and software developers like SimScale. So I think it's been a successful model of a partnership, right? How we use SimScale's capabilities in the cloud, software development, etc., to bring the expertise that's needed in the industry to drive forward the change which Beyond Carbon is doing. So thanks so much to Beyond Carbon for everything you've done. I'm now going to hand over back to Darren Lynch.
Okay, thank you, Nagman, for taking over the QA session there, and thank you very much for participating with Chris and Ramya. I guess it must have been a fantastic Q&A session. We're slightly over time, but just to answer the final question on meshing refinements that Nagman asked me to quickly touch on. Yes, the SimScale platform does support the full range of meshing refinements that you would expect. So that includes region refinements, surface refinements, sweep meshing, even more global controls over the automated meshing as well. So I'm sure Chris and myself will also be talking about methods of bringing that into the current workflow. In terms of next steps for this webinar, firstly, let me just say thank you a huge amount to Chris, Ramya, and the whole team at Beyond Carbon for putting together such amazing content for this session. Where we go from here, you can actually visit our website, sign up to simscale.com. You can contact us directly at sales@simscale.com. What will actually happen then is we'll get in touch with you within a couple of days and talk about your simulation needs and you can, of course, reference this webinar, and we'll make sure that we come prepared accordingly. For those that are joining us that are already SimScale customers, then simply just talk to your customer success or customer success managers as to how we can actually get this in your hands, essentially. We would be more than happy to do some sort of early access to our current AEC customers in the very short and near-term future. Thank you very much for everyone who's joining. Sorry for the slight audio issues that I seem to be having, but hopefully it didn't spoil the experience too much. If you've got any further questions, do feel free to reach out to us. And with nothing else to say, have a great afternoon, and I'll catch you next time.